10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Hello student, good evening to all of you, and let us continue our chapter number 10, circles. In our last period we have discussed about theorem number 10.3. Let's see it again. The perpendicular from the center of a circle to a chord bisect the chord. Okay, so now next point, what is the converse of this theorem? So to write this, first let us be clear what is assumed in theorem number 10.3 and what is proved. Given that the perpendicular from the center of a circle to a chord is drawn, and to prove that it bisects the chord. Thus, in the converse, what is the hypothesis? So if a line from the center bisects a chord of a circle, and what is to be proved is the line is perpendicular to the chord. So the converse is as theorem number 10.4, that the line drawn through the center of a circle to bisect a chord is perpendicular to the chord. That means if we have circle with the center O and if this line drawn through the center of the circle, and if this line if bisect chord AB, that means AM is equal to BM, then the line L or OM is perpendicular to the chord. This says theorem number 10.4. So next, see here. Is this true? What is theorem number 10.4? So try it for few cases and see, you will see that it is true for these cases, and see if it is true in general by doing the following exercise. We will write the stages and you give the regions. Okay, so let AB be a chord of a circle with center O, and O is joined to the midpoint M. AB, you have to prove that OM is perpendicular to AB. So this is given and you have to prove this. Now see here, for triangle AOM and triangle BOM. So AO is equal to BO, radius of the circle. AM is equal to BM is given. See here is given. AM is equal to C1 BM and OM is common for both triangle. So therefore triangle AOM and triangle BOM are congruent, and therefore angle AMO is equal to angle BMO by CPCT. So, but angle AMO plus measure of angle AMO plus measure of angle BMO is equal to 180, because angle of linear pair, and so therefore equal and 180, that means measure of angle AMO is equal to measure of angle BMO is equal to 90 degree, and therefore OM is perpendicular to AB. So see here, we have to prove that OM perpendicular to AB. Now see here, join OA and OB, see the figure. In triangle OAM and OBM, OA is equal to AB, radius of a circle, AM is equal to BM is given, and OM is equal to OM is common. Therefore, both triangle OAM, OBM are congruent by congruence rule of SSS. Therefore, angle OMA is equal to angle OMB 90 degree by CPCT. And therefore, but measure of angle AMO plus measure of angle BMO is equal to 180, because this is angle of linear pair, and therefore measure of angle AMO is equal to angle BMO is equal to 90 degree, because equal and sum is 180, therefore each must be 90 degree, and therefore OM is equal to OB. This is 90 degree, and therefore this we have to prove. Now next point, circle through 3 points. So you have learned in chapter number 6 that 2 points are sufficient to determine a line. Okay, but that is, there is one and only one line passing through 2 points, and natural question arises that how many points are sufficient to determine a circle. Okay, then take a point P, and how many circles can be drawn through this point. You see that there may be as many circles as you like passing through this point. See here, circle 1, 2, 3, 4 and as many as passing through the given single point P. So now take 2 points P and Q. You again see that there may be an infinite number of circles passing through P and Q. See here. So what will happen when you take 3 points A, B and C? So can you draw a circle passing through 3 collinear points? See here what happened. When we take 3 points and all 3 are collinear, then one point is outside of the circle. No, we cannot draw. So if the points lie on a line, then the third point will lie inside or outside the circle, passing through 2 points. So let us take 3 points A, B and C which are not on the same line, or in other words they are not collinear. So what happens? See here, 1, 2 and 3, A, B and C, 3 points. So draw perpendicular bisector of AB and BC, say PQ and RS respectively, and this perpendicular bisector intersect at one point O. Not that PQ and RS will intersect because they are not parallel. See here like this. So if you have 3 points, just 1 minute, let me set the camera. I think now it is okay. Okay. So 3 points A, B and C. So take, construct this line and this line also. So this is the center. See here, but you have to construct perpendicular bisector as we have already studied in our chapter number 11. Okay, so now O lies on the perpendicular bisector PQ of AB. You have OA is equal to OB, and as every point on the perpendicular bisector on a line segment is equidistant from its endpoints, and we have it proved in chapter number 7. Similarly, as O lies on the perpendicular bisector RS of BC, you get OB is equal to OC. That means OA, OB and OC all are equal, which means that the points A, B and C are at equal distance from the point O. So, if you draw a circle with center O and radius OA, it will also pass through B and C, and this shows that there is a circle passing through the 3 points A, B and C which are not collinear. So you know that two lines perpendicular bisector can intersect at only one point. So you can draw only one circle with this radius. This radius, that means OA. And in other words, there is a unique circle passing through A, B and C. And this is theorem number 10.5, that there is one and only one circle passing through three given non-collinear point. So no one is other, only one circle can pass. There is one and only one circle passing through three given non-collinear points. So here, if ABC is a triangle, then by theorem 10.5 there is a unique circle passing through the three vertices of given triangle. ABC is A, B and C of the triangle, and this circle is called the circumcircle of the triangle ABC, and its center and radius are called respectively the circumcenter and the circumradius of the given triangle. So you can draw a circle passing through three vertices of the given triangle. Now next point is equal chords and their distance from the center. So let AB be a line and P be a point. Since there are infinity number of points on a line, so if you join these points to P, you will get infinitely many lines. See your first figure. What says AB be a line and P be a point. So where is P and where is the point? P is outside of the line. So PA, PL1, PL2, PM, PL3, PL4, PL5, PB. Okay. So namely PM is the perpendicular from P to AB, is PM will be the least. In mathematics, we define this least length PM to be the distance of AB from P. That means the distance from AB from P is perpendicular line from the given point. So you may say that the length of the perpendicular from a point to a line is the distance of the line from the point. Not that if the point lies on the line, it is obviously the distance of the line from the point is 0. So a circle can have infinitely many chords. You may observe by drawing chords of a circle that longer chord is nearer to the center than the smaller chord. Okay. See here, this is center. This is longer one and this is smaller one. So AB and CD, AB is less than CD. So distance from the center, see here, longer one is nearer to center. So if here is M, here is N, therefore OM is less than ON. It is cleared. And therefore we can say that longer chord is nearer to center than the smaller chord. So you may observe it by drawing several chords of a circle of different lengths and measuring their distance from the center. So what is the distance of the diameter? What is the distance of the diameter, which is the longest chord from the center? Obviously, since the center lies on it, the distance is 0. So do you think that there is some relationship between the length of the chord and the distance from the center? Okay. So do this activity. Draw a circle of any radius on a tracing paper. Draw two equal chords AB and CD of it and also the perpendiculars OM and ON on them from the center O, and fold the figure so that D falls on B and C falls on O, and you may observe that O lies on the crease and N falls on M. Therefore OM. So see here, this is AB and draw so the bigger one, see here, take AB and CD. Okay, so both are chords. So AB and CD, and D falls on B and C falls on A. Just like this. See here. See here. Here is M and here is N. So OM is equal to ON. So now see this figure. O is the center of circle. AB and CD are are chord of the circle. OM and ON is the distance from the center. So repeat this activity by drawing congruent circle also and with center O and O dash and taking equal chord AB and CD on each. See here like this and this. So the conclusion is that equal chord of a circle or of congruent circles are equidistant from the center or centers. So if you take two congruent circles, then center. Equal chords of a circle are equidistant from the center or centers. So that activity, let me show you again that this is A, this is B, this is C, and this is D. So see this activity again, that this is called AB, this is called CD, and this distance is OM, this is ON and this is OM. So O is here. Now fold this paper. So see here, this is A and this is C. Here B on D and M on N, and that means ON is equal to OM. So you can easily understand that equal chord of a circle or congruent circle are equidistant from the center or centers. Next, it will be seen whether the converse of this theorem it is true or not. And for this, draw a circle with center O. From the center O, draw two line segment OL and OM of equal length and lying inside the circle. See here like this. Here OL and OM are equal. So then draw chord PQ and RS of the circle perpendicular to these lines OL and OM respectively, and measure the length of PQ and RS. Are these different? No. See here like this. If OL and OM are equal, then PQ and RS are equal. Yes, both are equal. Repeat the activity for more equal line segment and drawing the chord perpendicular to them. This verify the converse of the theorem that what's that? So if chords are equidistant from the center of the circle, then the chords are equal. So this says theorem number 10.7, chords equidistant from the center of a circle are equal in length. That means if chords are equidistant from the center of a circle are equal in length. So in our next period we will solve some sums of exercise number 10.4, okay, on tomorrow. So till then, goodbye student, and try to understand all this theorem, statement of this theorem. Okay, so we will meet you on tomorrow. Thank you.